everybody, my name is Joshua Panek, and today I'm going to be going over the ParmeSan Sanitizer-guided Greybox fuzzing. We'll be going over what it is and how to better understand it. Before we get into the finer details, I'll be going over the background behind fuzzing, the main design of ParmeSan, why it improves bug discovery speed, and finally we'll be going into some limitations of the approach. It's important to note that the ParmeSan is Sanitizer-guided, which we'll go into more detail later in this presentation. And the main goal with fuzzing is to find vulnerabilities, and we want to do it at a faster method. And traditionally, fuzzers are doing this by exploring as much code as possible. However, this strategy can waste time and resources, so we can look at sanitizing as a way to speed the process up. So, to begin, we'll look at a basic overview of fuzzing and what can be done to make it better. So, fuzzing is an automated technique used to discover vulnerabilities in a software. It works by generating large numbers of inputs and feeding them into a program to see if something breaks. This is demonstrated in this little graphic here. So you can see this is a very highly simplified version of what a fuzzer looks like. And essentially it's just, as I said, taking these random inputs, putting it into programming, and then hopefully waiting to see if we get a crash from it. This approach is successful in security testing when it discovers vulnerabilities, as once a vulnerability is discovered, it can be used. For one, you can either use it for your own testing purposes if you're testing your own program, and also against other programs if you are going into the cybersecurity or cyber warfare area. However, there is a challenge with fuzzers, as a lot of them rely on code coverage as a metric, meaning basically if more code is being covered by the fuzzer, then the belief is that more bugs will be revealed that way. And the problem with more code coverage is that it does not directly correspond to bug coverage, as many executed paths may not contain vulnerabilities at all. So what this leads to is fuzzers spending a lot of time exploring safe code instead of focusing on areas where bugs are more likely to occur. This brings up an interesting question. If a fuzzer covers 90% of a program's code, do you think that it'll guarantee it will? Do you think that guarantees it will find the most bugs? So now that we've gone into a little bit of a basic overview of fuzzing, we can begin to break it down into the different types of fuzzing. Then there are three main types that we can look at here. For one, there's black box fuzzing, which is the most rudimentary of them all. Essentially what this is it is generating random inputs without having any understanding of the program at all. So just imagine taking a random array of bytes or anything and just throwing it, and it's like throwing spaghetti at a wall until it sticks. This type of fuzzer is not very difficult to implement at all, but the downside to this is that it is extremely inefficient, as you can think about the math of randomly generating inputs and whether or not that will actually end up working. The next is kind of the opposite end of the spectrum, which is called white box fuzzing. And this technique uses things like symbolic execution to analyze program behavior and generate inputs that trigger specific paths. This does have some issues, as it is kind of looking to narrow down how to actually access the vulnerability rather than just spray and pray. However, it does suffer from scalability. With black box, is extremely scalable. You can apply it to nearly everything. However, here it is a lot less easy to apply scalability and also compatibility. When it's more narrow to a specific program, it doesn't necessarily apply to everything. And next we have Greybox, which is essentially the middle ground or the compromise between black box and white box fuzzing. It utilizes lightweight feedback, and also, it utilizes lightweight feedback and coverage information to guide the input generation. So basically, it's not just being random, and it's actually utilizing what the program is saying to make the process better. And the biggest thing from this is that while it may not be the best thing possible, it certainly is the most practical. For examples of modern fuzzers that fall into this Greybox category, you have things like AFL and Agora. Both of these are going to be benchmarks that are used later on to compare how ParmeSan does against other Greybox fuzzing. So now that we've kind of discussed what Greybox fuzzing is, we can go a little bit more in depth into some issues that are presented with them. And similar to what I was saying earlier with the spray and pray technique, this is one of them, being called the coverage-guided fuzzer. And essentially what this is operating under the assumption that more coverage increases the probability of finding bugs. The thing is that this assumption isn't always efficient. One example I like to think of, and I included this graphic of splash of paint, is say you have a wall and there's a very specific part of the wall that you want painted. However, you are blindfolded, and instead of just maybe picking a few spots here and there to paint, you decide to take the paint bucket and splash it against the entire wall. Now, while it is likely that you do end up covering the spot you wanted to paint, you also have to consider that now the entire rest of the wall is also painted, and sure, while that may be much of an issue, you've also just wasted an entire bucket of paint. And how this relates back to fuzzing is how time is spent, and fuzzing is going to spend a lot of time exploring, and a lot of this time could be spent exploring irrelevant parts of the program before it actually finally reaches the vulnerable code. And this issue leads to a metric called time to exposure, or TTE, which is essentially measuring how long it takes a fuzzer to trigger a bug. Reducing TTE is one of the main goals of this research. And the question to ask is, if you were designing a fuzzer, how would you decide which parts of the program are more likely to contain a bug? So on the other side of Greybox fuzzing, we have directed fuzzing. Think of this as kind of the opposite approach to the last example. In this one, Directed fuzzing is attempting to solve the problem by focusing fuzzing towards specific code locations. An example of this is the fuzzer like AFLGO, which can target newly modified code or security patches. This approach works well when you already know where potential vulnerabilities might exist. However, directed fuzzing also has limitations. It focuses only on specific targets and may miss vulnerabilities in other parts of the program. So it can underestimate overall bug coverage. And in this analogy here, I'm thought of how it's like you have a target and you know for sure that that is a target you want to hit, so it's not too difficult to hit with your bow and arrow. However, that may blind you from other targets being in the area, and you may not necessarily pick them up initially as you are too focused on one thing. So how does this tie into ParmeSan and its key idea? Well, the key idea is surprisingly simple. Basically, we're taking the best of both worlds and combining it into a way that we're able to explore places of high likelihood while also not suffering from the downsides of direct fuzzing and coverage fuzzing. And the way to do this is by utilizing sanitizers. Most modern compilers include sanitizers that direct common programming errors like buffer overflows or use after free bugs. These sanitizers insert runtime checks into the program to detect violations. The authors of this paper for ParmeSan realized that these checks can also be used as signals for where bugs might occur. So instead of just using sanitizers to detect bugs, ParmeSan uses them to guide the fuzzing process towards those potential bug locations. And this provides a balance between directed fuzzing and coverage-based fuzzing. But you may be asking, or you may not be super familiar with what a sanitizer actually is and how it works. So, what are sanitizers? Well, sanitizers are compiler-based tools that detect runtime errors. So think about, in your computer systems class when you're running a C program, and before you run it, you have to compile the program, and say you compile it, but then it gives you a list of errors that it is saying you have to remove before you can actually run the program. Essentially, that's kind of what is going on here. And some examples, as I said, with like you're just compiling a program. It could be memory errors, undefined behavior, or detecting type confusion. And when the compiler builds a program with sanitizers enabled, it inserts additional checks throughout the code. And in this graphic here, you can see that we take the original code, it goes into the compiler to add checks, and if the program violates any of one of these conditions from these checks, then the sanitizer will report the error. And ParmeSan is utilizing the locations of these checks as potential targets for fuzzing. So here is what the ParmeSan architecture looks like. Now I know this is probably not super easy to interpret right now, especially not knowing what the major components are. And to alleviate this problem, I'll be going ahead and simplifying it and breaking down the components of this architecture. So here's a more simplified look of what the architecture looks like, and it mainly consists of three major components. The first being the target acquisition. This relates to the sanitizers that we just discussed, where this point is where we are identifying where the sanitizer inserted checks are and basically saying, okay, there might be a potential target here. The second is the dynamic control flow graph, or CFG, and this part is basically tracking how the program is executing and getting feedback from what is going on, so that as time goes on, as the fuzzer is running, as the program's running, we can get a stream of feedback, so we're not just shooting in the dark. And finally is the fuzzer itself, which is basically taking in the inputs from the target acquisition, moving it towards the location of the sanitizer checks, and then sending it to, or checking in with the dynamic control flow graph to get feedback. And together, these components create the feedback loop that we're looking for, which guides the fuzzing towards likely vulnerabilities. So the first thing we can look at with all the components that we just discussed is target acquisition. Basically what this is it is in place to automatically identify interesting fuzzing targets. So what's going to happen is, on the first step, the program is going to compile twice. The first time it'll compile normally, and the second time it'll be with the sanitizer instrumentation. And by comparing the differences between the two, we can identify the code locations where sanitizers inserted checks, and these are locations where bugs are more likely to occur. The system also applies a pruning technique to remove targets that are unlikely to contain bugs, such as frequently executed code paths. So if there is a method that is being executed a lot, then it's probably not going to contain a bug. The next component is the dynamic control flow graph. Now this image here is just a generic example, doesn't necessarily relate to the project. However, directed fuzzers need a control flow graph to estimate how far a program execution is from a target. So for instance, if we start at A and a target is at, say, D, then we can say the distance is 2 or something like that. And that basically is able to help us narrow down how far we have to look, and that if we can stop at a certain point rather than keep going down. So most fuzzers will build this graph statically. However, the static graphs can be inaccurate, especially for programs with indirect function calls. So to alleviate this, ParmeSan instead constructs the control flow graph dynamically during execution. So it is getting feedback and changing. This produces a more precise model of the program's behavior, and it helps the fuzzer calculate better paths towards sanitizer checks. A big part that plays into the whole architecture as well is the data flow analysis, which is a big thing that ParmeSan utilizes, mainly to determine which input bytes affect specific programming conditions. So in this graphic here, we see we have some input and it is going towards a branch condition. So think of this like your if-else statements. And if we take a look at that and say, okay, these certain bytes, we're able to make some progress here and there, so therefore we're going to take this and use it as modification. Instead of randomly mutating the entire input, we can only modify the parts of the input that actually matter. and this dramatically reduces the number of executions needed to reach the target. So the next thing, now that we've gone over how everything works and falls into place, we can talk about what the strategy is, right? We have all the components, but how does it all work together? And basically, this strategy or process can be broken down into 3 stages. First is with ParmeSan exploring the program initially to build the control flow graph. This gives us sort of a base plate to go off of. Next, it performs the directed fuzzing towards the sanitizer targets acquired from the target acquisition. And then finally, once we reach those targets, we can focus on triggering what these sanitizer checks were originally existing for to expose these bugs. And this combination allows the system to reach vulnerabilities more quickly than traditional fuzzers. And we can see this in the actual results. So as I mentioned earlier, there were some Greybox fuzzers that would be used as benchmarks for the ParmeSan fuzzer. And the authors evaluated ParmeSan against a few of these. The biggest ones that stood out were Angora, which found bugs 37% faster, and another one being the AFL Go fuzzer, which had a significant and very large improvement of 288%. So overall, ParmeSan is able to discover bugs significantly faster than some of its inspirations, and this improvement mainly comes from focusing the fuzzer efforts on sanitizer instrumented code rather than just blindly maximizing coverage, which we find in Greybox techniques. So now that we've kind of gone over all the aspects of ParmeSan, we can also talk about the limitations, as not every fuzzer or not every program is going to be absolutely perfect. So the biggest thing is the sanitizers available at the time. Not all sanitizers are built the same, and some bug types may not be detected by sanitizers, and thus being a major factor into ParmeSan. Not having a good sanitizer will lead to it not finding targets as effectively. The second is the approach relies on LLVM intermediate representation, which may limit compatibility with certain binaries. Additionally, or finally, the sanitizer instrumentation introduces runtime overhead, or in other terms, it's doing extra work while running when it could be better. So what are some key takeaways of this whole paper? Well, for the most part, the paper introduces a new fuzzing strategy that uses sanitizer instrumentation to guide fuzzing towards likely vulnerabilities. This approach greatly bridges the gap that exists between coverage-guided fuzzing and directed fuzzing. By focusing on sanitizer checks, ParmeSan reduces the time needed to discover bugs. That is all I had for my presentation. Thank you for watching.